Our primary purpose in studying the history of physics is to understand the method of inductive logic, to understand the method of how we can gain scientific knowledge from observations. And the main aspect of inductive logic we're going to understand by looking at the history of physics is to understand how each idea is stacked on top of each other idea, each serving as the foundation for the next. And so if you're going to understand this part 2 of our brief history of physics, I encourage you to watch part 1 first, since everything we'll talk about today is based on what we learned in the first video. Now, to start us off, I'm going to take us all the way back to the time of the ancient Greeks. And one question that the ancient Greek philosophers asked was, what are materials made of, and why do different materials have different properties? As Greek philosophers thought about materials and how they changed, they realized that the phenomenon of change itself seemed to be a kind of problem. In the case of change, something becomes what it isn't. So philosophers ask the question, how can something be what it is and then also become what it isn't? Now, if this sounds kind of like a technicality or a word game or kind of silly, let me put it to you this way. A man cannot simply, poof, transform into a rock. A rock can't simply, poof, turn into a pink elephant. Yet we see things change all the time. We see wood when it burns turning into ash. We see water when it evaporates over time, turning apparently into air. So how is it possible for something to be one thing in one moment and then something else the next moment? Well, Parmenides' solution to this problem was that nothing actually changes. Since we know everything is what it is, nothing can become what it isn't. So change must somehow just be an illusion. On the contrary, says Heraclitus, we can see that everything changes, so it must be identity that's actually an illusion. Nothing is what it is, since we can see everything becoming something else. Now, eventually this problem was solved in principle by the philosopher Democritus. Democritus proposed that all materials are made of atoms, are made of little indivisible pieces of matter, and that there are many different kinds of atoms. And each of these individual pieces, each of these indivisible atoms are unchanging. But when we see change, when we see a log turn into ashes, when we see various kinds of changes in nature, what we're witnessing is the rearrangement of these unchanging atoms. And so through this kind of hypothesis, which Democritus sort of thought up without any direct scientific evidence, through this hypothesis, we were able to see how change and identity could exist at the same time. Now, to continue the story of the science of materials, we're going to fast forward past the Romans, past the Dark Ages, all the way to the time of Galileo, to our next hero, Evangelista Torricelli. Torricelli was a student of Galileo, and he had been tasked with trying to understand suction. He's trying to understand when you suck the air out of a straw, then water will come up through the straw into your mouth, right? Torricelli experimented with this using vacuum pumps. And what people had found is that no matter how good your vacuum pump was, when you pump the air out of the top of a chamber like this, it'll make the water come up, but it'll only ever rise to about 10 meters. And no matter how good your pump is, you'll never get the water to rise past that level. So Torricelli was trying to understand why this is the case. And the way he understood this is he realized he thought to ask the question, well, why does the water even rise to begin with when you pump the air out of the top? And he thought of the idea that maybe it's rising because the air above us is actually pushing down, and that pushing down pushes down on the water, which in turn makes the water want to squirt upward. Now, when the air is in the way in this chamber, then the water won't squirt upward, but there's air in the way. But if you remove the air from the chamber, then the water will go ahead and squirt right upward. And Torricelli thinks of an experiment to test this hypothesis. If it's the case that this force pushing the water up is caused by a bunch of air stacked above us, then the air stacked above us must weigh the same as about 10 meters of water. So what he does is he makes a new tube, but this time this tube is filled with mercury. And he calculates that 76 centimeters of mercury weighs the same as 10 meters of water. And what he does is when he takes a tube of mercury, fills it full, and then tips it upright, he finds that the mercury will drop until there's only a height of exactly, as he predicted, 76 centimeters of mercury standing above his little pool. And so by doing this, Torricelli was able to conclude that we live submerged at the bottom of an ocean of air. We see that through scientific reasoning, by putting together the pieces of what we know to try and understand observations that we don't yet understand, the inductive process allows us to understand the unseeable. Torricelli is able to prove that there's this enormous pile of air above us, and it's weighing down on us with the weight of 10 meters of water, even though we can't literally see this air or really feel the weight of it. Now, our next hero is Robert Boyle. And Robert Boyle saw Torricelli's experiment, and he understood it, and he thought about this and realized, this is interesting. Air produces pressure. It pushes on things because there's a big stack of air above us. It's a fluid, and it's one thing stacked on another, stacked on another. But if you look at the top of this chamber Torricelli made, there is no air stacked above it. The air is confined to a chamber up there in the top. Yet before you suck the air out, that air is able to hold the water at bay with pressure. So it must be the case that at all times, air is pushing in every direction. It's exerting a pressure in every direction. And so Robert Boyle wants to understand this expansive force that air is able to exert. And so what he does is he squeezes the air. Robert Boyle puts a little pocket of air into an apparatus like this and pours mercury into it. The mercury pushes on this little pile of air, and he's able to find the following relationship. Robert Boyle finds that the more pressure you put on the air, the smaller it becomes. And so he finds this relationship. We can see in this formula that if we make the pressure larger, that means that the volume has to be smaller according to the formula. Now, what he also finds is that in general, on hotter days, the air pocket wants to be larger than on colder days. So what Boyle then does is he goes to this little pocket of air in his apparatus and he holds a candle up to it, and he finds that this actually expands the size, the volume of the little pocket of air. And so apparently heat makes air expand. Now, unfortunately, Boyle was unable to measure the effects of temperature on air because he didn't have an actual way of measuring temperature. The thermometer hadn't been invented yet. So all he could say is, I made it hot and it got bigger. People could measure temperature just sort of by feeling it, like, oh, today's pretty hot or today's pretty cold. But other than that, they couldn't really measure it. There was no number that they could assign to different temperatures. Until, of course, we have our next hero, Daniel Fahrenheit, who invented the thermometer. Daniel Fahrenheit invented a mercury thermometer when he noticed that mercury expands when it's hot and contracts. It gets smaller when it's cold. And so what he did is he simply put mercury into a tube. This probably looks familiar. He put mercury into a tube, and when it expands, it crawls up through the tube. And by marking different areas of the tube, by marking different locations on the tube, we're able to identify different numbers for the different temperatures. This then allowed two of our next heroes, Jacques Charles and Guy Lussac, to perform certain experiments on trapped air and heat them and cool them to see what would happen to their properties. And Jacques Charles found that an increase in the temperature of air will increase its volume when you hold the pressure constant. Gay-Lussac, on the other hand, when he held the volume of the air constant, found that increasing the temperature increased the pressure of the air. So we have an interesting model of air here. If you put all of these relationships together, Boyle's law, Charles' law, and Gay-Lussac's law, if you put them all together, you get this relationship right here. You can put them all together. And what we find is that we get a very interesting perspective on air and the way it behaves. If you squeeze air, the smaller you make it, the harder it pushes out. Similar to a spring. You can think, and this makes people think, well, maybe air is like maybe like a network of springs, because the more you crush it, the more it pushes back on you. The smaller the volume, the greater the pressure outward. But then there's a problem with this sort of model or analogy. Apparently, these springs get stronger if you make the gas hotter. So that doesn't seem to really explain that much. So we understand the behavior of air at this point, but we don't understand what about air causes it to behave in this way. Now, while some scientists were studying the physical behaviors of materials, such as gases, other scientists were trying to understand changes in the materials, how one material can turn into something else. This is something that people had been observing sort of on an unscientific level for a very long time. For example, bronze can be manufactured by mixing copper and tin. Similarly, cooking iron will actually change it into a harder material called steel. And rotting plant matter of certain kinds produces a fluid which is very fun to drink. So the question is how do these changes in the constitution of materials, how do they happen? And there were some men known as the alchemists who sort of played around with these different changes and tried to manipulate them with the ultimate goal of creating gold out of baser metals such as lead. This was a dream of theirs. But a lot of this alchemy was very unscientific. People were not approaching this with a disciplined, empirical kind of scientific method. But luckily, a man came along, Anton Lavoisier, who figured out principles of chemistry, who laid down certain principles that we have to just follow when we're conducting chemical investigations. And some of these principles are, for example, that materials cannot transmute. Now, what does this mean? Lavoisier says, if one material turns into another material, it's not okay to just say that the change was spontaneous. It's not enough to just say, oh, well, we had one material and then it just transmuted. It just changed for no reason into a different material. This is sort of lazy thinking, right? And it goes against the kind of argument that the ancient Greeks would have validly have. Something can't just change into something else for no reason. There has to be some aspect of its identity which caused the change. And you remember that Democritus offered one way that this might work. Maybe the atoms themselves are unchanging, but it's their relationship to one another which changes and causes the changes that we see around us in matter. So Lavoisier says no transmutation. We can't. If something changes, we have to account for what caused it to change. Now further, Lavoisier also put forth a principle that matter cannot be created or destroyed. And so similarly, something that is cannot become nothing. And you can't have something popping out of nothing. And so Lavoisier, by laying down this principle, he was able to put forward a very practical method of chemistry, which is that you need to weigh the stuff that goes into your reaction and you need to weigh the stuff that comes out of your reaction. And if they don't agree, it means you lost material somewhere. Maybe a gas was produced by your reaction and you didn't capture the gas, or maybe you lost material through some other means. And so you have to keep track of these things. Otherwise, we're never going to be able to figure out how some kinds of matter can interact and change into different kinds of matter, because we won't be accounting for all of the different exchanges of ingredients. And finally, another principle that Lavoisier put forward was the difference between elements and compounds. As the alchemists and early chemists were examining chemical change, they found that the mixture of some things can produce other things, and that certain materials can be broken down into other materials. And Lavoisier made a very important conceptualization here. Elements, says Lavoisier, are materials which we haven't found a way to break down yet. We haven't found a way to turn them into two or more other materials. Whereas compounds are materials which are found to be manufacturable using a combination of two other known materials. So for example, water is a compound because it can be broken into oxygen and hydrogen. Whereas hydrogen and oxygen were found to be elements because through no known chemical process could they be broken down into other components. And so Lavoisier, by identifying these basic laws, was able to put chemistry on a very strong foundation as it moved forward. This allowed chemists to be much more systematic when trying to understand chemical changes in particular reactions. Now, over the course of weighing the products and reactants of many different reactions, one chemist, Joseph Proust, found his law of definite proportions. And this gave us a huge hint into the basic nature of matter. Proust found that in a number of different chemical reactions, the elements in those reactions would always combine in particular weight proportions. For example, with the synthesis of water, we find that for every 1 gram of hydrogen we have to react 8 grams of oxygen. To create fixed air, which is carbon dioxide, that's what we call it now, we find that for every 3 grams of carbon, we have to put in 8 grams of oxygen. So it's almost like these compounds have recipes. You can't just blend the materials together in any ratio you want. It's that this recipe calls for 2 eggs, and if you have 3 eggs, then that third egg simply has to be set aside as the reaction progresses. So if you react 2 grams of hydrogen with 8 grams of oxygen, the 1 gram of hydrogen simply won't react. It'll still be laying around and it won't go into the resulting water. And so finding that these reactions had consistent mass ratios or consistent weight ratios going into the reaction, this allowed John Dalton, by cross-checking the different proportions of different reactions, Dalton thought that Democritus was basically onto something, that maybe what's going on is that the reason these elements always combine in certain ratios is because at the basic level, they're made of atoms. They're made of little particles. And each of these different elements, their respective atom, has different weights. And so as a result, when they combine, they can only combine in certain definite proportions. And so by cross-checking all of these reactions against one another, Dalton and other chemists are able to come up with proposed weights for the different atoms. So hydrogen, it was found, is apparently the lightest element, while other elements are always multiples of the weights of hydrogen. So it's found that oxygen has a weight 16 times that of hydrogen, and carbon is found to have a weight that is 12 times the weight of hydrogen. And what they find is that by applying this hypothesis to many different reactions, it seems to be consistent with all of them. So this is very good evidence for a theory of atoms. Further, a lot of chemical reactions were found to occur when the chemicals were in a gaseous state. Henry Cavendish, for example, took hydrogen gas and oxygen gas, put them in the same container, lit them on fire. It would produce this big flame, and in the bottom of his reaction chamber would be a little puddle of water. What was then found is that in general, there's a law of combining volumes. With all of these different gaseous reactions, there's different rules for the amount of volumes proportions of different gases which would combine with one another. For example, in the synthesis of water vapor, like Cavendish's experiment, he found that 1 liter of oxygen gas plus 2 liters of hydrogen gas would create 2 liters of water. So there were these very strange proportions of volumetric combination and result that we found that were always consistent across all of these reactions. All of these different patterns that were found in the reactions allowed chemists to come up with the atomic theory of matter, which is that elementary substances are made of indivisible units, each called atoms. And these atoms can link together to form specific kinds of molecules, each of which are the basic units of compounds. And this theory was completely consistent with the fact that compounds are always formed of definite proportions of elements. Further, if we make the assumption that the volume of a gas is always proportional to the number of particles in that gas, again, not the number of atoms in the gas, but the number of particles, whether those particles are atoms or molecules. If we make that assumption, then all of these gas reactions start to make sense. For example, if we have 2 liters of hydrogen gas, which consists of molecules of 2 hydrogens, and 1 liter of oxygen gas, which is also diatomic, it's a molecule made of 2 oxygen atoms, then it makes sense why 2 liters and 1 liter could come together to make 2 liters of water vapor. And the reason is because these molecules are combining together into a single water molecule. And so as a result, we actually get less particles at the end of the day during this reaction, which results in less volume. So the atomic theory of matter seems to account for a lot of these strange and very particular patterns that we see in the realm of chemistry. We'll find that this atomic theory of matter ends up being completely consistent with the sciences of heat, which we will now explore. So let's think about heat. It seems like heat is this stuff which causes things to get hot. And here's why people thought that heat might be a stuff. If you think about how one thing causes another thing to get hot, it always comes at the expense of the hot thing. So for example, if you take a hot piece of metal and you dunk it in water, then the hot metal will cool and the water will warm up. So the heat so it must be that heat, or it might be that heat is this stuff that goes from the metal into the water. So the water heating comes at the expense of the metal thing cooling. To test this hypothesis, scientists committed experiments in the realm of calorimetry, which is the study of heat transfer. What they'd find is they would isolate certain materials and put them in contact with one another and find out how the temperature drop of one object is correlated with the temperature rise of a second object. And what they found is that this formula always seemed to describe the change in temperature of two objects. So here we see that the mass on one side of this equation indicates the mass of the object which is losing heat. The mass on the other side of the equation indicates the mass of the object that is gaining heat. And so what we find is that the larger an object is, the harder it is to heat up. The more heat is required to actually change its temperature. So for example, if you take a tiny bit of hot water and pour it into cold water, it won't change the temperature of the mixture very much. On the other hand, if you take equal amounts of hot water and cold water, the temperature will sort of settle somewhere in the middle. It'll settle exactly in the middle, in fact. Now, another thing that is found is that different materials have a different C, or heat capacity. And the heat capacity indicates how hard it is for heat to change the temperature of that material pound for pound. Water all other things being equal, is very difficult to change the temperature of. Metal, on the other hand, is easy to change the temperature of. It doesn't take that much heat. So if you place a 1 kilogram piece of metal in thermal contact with 1 kilogram of water, then the metal will change its temperature greatly while the water will not. So it would appear that heat, like matter, is a substance that can be neither created or destroyed, but simply transferred from one object to another, changing the temperatures of those objects. But there's really strong evidence against this hypothesis. Let me demonstrate. Do this. You can make heat, apparently, just by rubbing objects together. Now, a lot of scientists didn't like the idea that heat could simply be created from nothing, so they didn't buy this for a long time. But the chemist Humphrey Davy did an experiment where he isolated 2 blocks of ice, thermally isolated them so that heat could not leave this chamber with the ice or get into the chamber with the ice. And he rubbed these 2 pieces of ice together, and it was found that they melt. So apparently you can create heat from nothing just by rubbing things together. And this made people think maybe heat is a form of the motion, the internal motion of the little atoms that materials are made out of. And our next hero took this possibility very seriously. His name was J.J. Waterston. Waterston was trying to understand the behavior of gases. Remember how gases obey this formula, and we know this from experiments, but we don't know what it is about gases that causes them to obey this formula. And Waterston, his hypothesis was, he looks at this and he says, okay, well, if heat is just a form of motion, and materials, including gases, are made of particles, of molecules and atoms, well then perhaps the pressure is just the continuous forces of all of the different atoms hitting the sides of the container, pushing out, and this is what causes gases, including air, to push outward. Incidentally, it was found that this law of gases applied not only to air, but it applied to all chemicals in a gaseous state. And so Waterston says maybe this pressure is just the continuous bombarding of the little particles hitting the container. And further, we find, thanks to Gay-Lussac's law, that the higher the temperature is, the more pressure. So maybe temperature is just a measure of how fast the little atoms are moving around, and the faster they move, well, it stands to reason that they're going to be hitting the sides of the container harder and more often. So maybe, says J.J. Waterston, I can understand gases using nothing but the assumption that they are little atoms and molecules which obey Newton's laws. So what Waterston does is he works this out on paper. He says, let's just pretend that a gas is nothing but a bunch of bouncy balls bouncing around inside of a box, and that when they hit the sides of the box, they just obey Newton's laws based on just forces and accelerations. Let's assume that. And what he found was truly remarkable. He was able to get this equation. So where P is the pressure exerted by the balls continuously hitting the sides of the container, the volume is the size of the container, M is the mass of each of the individual molecules, and V is the speed or velocity of each of the individual particles. So the thing that's remarkable about this equation is that it looks almost exactly the same as the gas law that we already found empirically. And if it is indeed the same, this would seem to indicate that the temperature is just indicative of the velocity squared of each of the particles in the gases. And so this formula is truly remarkable because even though it hasn't been confirmed yet, it seems to put an actual mathematical relationship on the possibility that heat is nothing more than molecular motion. And one man who took this possibility very seriously was James Prescott Joule. Joule conducted an experiment where he takes a can of water, and this can is insulated from the outside world so that heat cannot go into the water or leave the water. He places a paddle in this water, a paddle that can stir the water around, create motion in the water. And he rigs this paddle up to a system of a weight which is allowed to fall and, in so doing, turn the paddle. Now, Joule knew certain other of Newton's laws which told us how much work would lead to how much velocity. So basically what work is it's force times distance. And it's found that a certain amount of work, a certain amount of force exerted over a distance will cause a body to pick up a certain amount of velocity. You can see the relationship pertains to its velocity squared. And so in Joule's situation that he rigged up, we can see that the force times the distance of his falling weight can be directly calculated. And that force times distance is transferred into this paddle. And each of the paddles, if the atomic theory is right, each of the paddles is going to be pushing the water molecules around in a circle. So what James Joule concludes is he says, okay, well, this should increase the squared velocity of the water molecules in direct proportion to the amount of work I put into the system, the amount of work I actually put into the water molecules. And since the velocity squared, according to Waterston, is just the temperature, then that means the amount of work I put into this system, the amount of work I put into the paddle, should be directly proportional to the change in temperature of the water. So James Joule conducts this experiment and he finds this is exactly what happens. He finds that the amount of force times distance of his falling object is directly proportional to the observed change in temperature of his water. So we can see that through the power of induction, through the power of reasoning from what we can see and building knowledge on top of knowledge, we're able to gain access to facts about the world that we cannot see. That matter is in fact made of atoms, and heat is nothing more than the motion of those atoms and molecules. And these two broad principles of science had a huge impact on man's life here on Earth. Thanks to the atomic theory of matter, we're able to understand how different atoms combine together to make particular molecules. This allows us to tailor-make chemicals to make stronger materials, specialized fuels, and life-saving medicines. By understanding how heat can expand gases, we're able to harness the expansion of gases to generate motion. This is called the engine. We have found that the burning of fuel can do the work of thousands of men, setting mankind free of muscular labor. But as we continue our journey, I think you'll find that these wonders are only the beginning. So I invite you to hit the subscribe button so that you can follow me on my journey as mankind continues his ascent from the swamp to the stars.